We'll start in 1 minute. In a few minutes, we'll start section 8.2 on area of a surface of revolution. But first, we'll do the last problem in section 8.1. In this problem, we're given the arc length function for a curve y equals f of x, where f is an increasing function. The arc length function is s of x equals the definite integral from 0 to x of the square root of 3t plus 5 dt. So if f of 0 equals 2, then find the equation for f of x. Okay, so we know that the arc length function has the form s of x equals the definite integral from a to x of the square root of 1 plus f prime of t squared dt. So what we do to start with, we set this integrand equal to 3t, or the square root of 3t plus 5. The integrands have to be equal. And then we'll proceed to solve for f of t with the initial condition f of 0 equals 2. Okay, so we set the integrands equal to each other. The square root of 1 plus the square of f prime of t. That's equal to the square root of 3t plus 5. Then square both sides, since each side involves a square root. When we square both sides, we get 1 plus the square of f prime of t equals 3t plus 5. Then subtract 1 from both sides. That leaves us with the square of f prime of t. That's equal to 3t plus 4. And then we'll take the positive square root. So f prime of t is the square root of 3t plus 4. Okay, then to find f of t, we just find an integral of the square root of 3t plus 4. So let's go ahead and replace t with x, since we're trying to find f of x. So f prime of x, I should say f of x, is equal to an integral of the square root of 3x plus 4 dx. So using the substitution rule, if u is 3x plus 4, then du is 3 times dx. So we we need 1/3 du equals dx. So upon making those substitutions, let's just leave it in terms of x. So bring the factor 1/3 out front. And then we have the quantity 3x plus 4 to the 1/2 times the 3 times dx. And then we can integrate that. We get 1/3 times 3x plus 4 to the 3/2 divided by 3/2. So if we divide by 3/2, that's equivalent to multiplying by 2/3. And then 3x times 3x plus 4 to the 3/2. And then plus a constant. We will use the initial condition f of 0 equals 2 to determine what the value of c is. Okay, so this is, we'll simplify this a little bit. 1/3 times 2/3 is 2/9. And then times the quantity 3x plus 4 to the 3/2 plus c. Okay, since f of 0 equals 2, we can write f of 0, replace x with 2, we get 2/9 times 4 to the 3/2 plus the constant. And this is equal to 2. Okay, so just a little bit more arithmetic. 4 to the 3/2 is 8. 2/9 times 8 is 16/9. So 16/9 plus c is equal to 2, but I'll write 2 as 18/9. So we have a common denominator, and so the value of c is 2/9. Okay, so up here in this space, I'll write what f of x is equal to. So f of x is equal to 2/9 times 3x plus 4 to the 3/2. And now we can replace c with 2/9. Okay, we'll go ahead and get started in section 8.2. Okay, in section 8.2, we discuss how to find the area of a surface of revolution. So this first sentence, revolving a curve about a line, forms a surface that is the boundary of the solid formed by the same revolution of that curve. So the goal is to come up with a formula for finding the area of a surface of revolution. So to start with, we'll find lateral surface areas of 3 geometric figures, 3-dimensional figures, right circular cylinders, cones, and frustums. And I'm going to use a lot of paper, so on other paper, we'll work on that stuff. Okay, to start with, a right circular cylinder. Well, that's like a soup can. So I tell you what that is so you don't have to guess what my drawing is. If you have a right circular cylinder, the top and the bottom are circles. We'll say that the radius of the circle at the bottom and the top is r, and it has a height. And we're just interested in the lateral surface area. That's the surface area that omits the circular ends, so the lateral surface area. Hey, if you were to cut this cylinder, forming right angles at the cuts, and then unravel it, it's just a rectangle. The length of one side of the rectangle is the same as the height. So my drawing is not quite to scale, but what's the length of the other side? Yeah, the length of this horizontal side is the same as the circumference of the circle. The radius of the circle is r, so the circumference is 2 times pi times r. And so this area, or the lateral surface area of the cylinder, is 2 times pi times r times h. Okay, the next object is a cone. So this is supposed to be a cone. So one side is pointed, and the other side is a circle. We'll say that its radius is r. And the distance from the point of the cone to the other end, forming a right angle at the bottom, we'll refer to that length as lowercase l. If you cut one side of this cone and unravel it, you get a sector of a circle. So something like that. The central angle, we will refer to that as theta. So the measure of that angle is theta radians. And these two straight sides are lengths L, though that's the same as the length of this side of the cone. And the length of this arc, well, this arc is the same length as the circumference of the bottom circle. So this arc length is 2 times pi times r. Okay, we know how to find the area of this sector, which is the same as the lateral surface area of the cone. So this sector is just a fraction of a circle with radius L. Okay, so the area of this sector, is a fraction of the area of a circle with radius L. So which fraction is it? The central angle is theta. A full circle has 2 pi radians. So the fraction is theta divided by 2 pi. And then we multiply that by the area of the circle with radius L. So this is pi times L squared. The pi's cancel, so we'll just write this as 1/2 times L squared times theta. Well, it would be nice to be able to replace theta with something in terms of the radius r and the lateral side length L. And there's a way that we can do that. Okay, this sector is just a fraction of a circle whose radius is L. And this arc length is just a fraction of the circumference of the entire circle. So this arc length, 2 pi r, is a fraction of the circumference of the circle whose radius is L. So what fraction is it? Theta over 2 pi again. So if we multiply theta over 2 pi and multiply that by the circumference of the circle whose radius is L, so the circumference of that circle whose radius is L is 2 pi L. So this is 2 pi times L. The 2 pi is canceled. 2 pi divided by 2 pi. And when we solve for theta, we get theta equals 2 pi r divided by L. Okay, so the lateral surface area of the cone, which is the same as the area of this sector, so I'll write this, the lateral surface area of the cone, which is the same as the sector, it's 1/2 times L squared times theta, but we're going to replace theta with 2 pi r divided by L. And then we do a little bit of arithmetic. 1/2 times 2 pi is pi. L to the second divided by L is r. What did I say? L to the second divided by L is L, and then we multiply that by r. So we get pi times r times L for the lateral surface area of a cone. So that's pretty nice. If you remember, we're not counting the circular end when we're finding the lateral surface area. But if we have a cone, and if we know the radius of the circular end, and if we know the length from the tip of the cone to the circle, then the lateral surface area is pi times r times L. Okay, now we can look for the area of a frustum, or the lateral surface area of a frustum. So what is a frustum? Well, the frustum that we're interested in is a cone with the top chopped off. So this is supposed to be a part of a cone where the top, there's like a smaller cone that's chopped off. So we have a circle at the bottom and a circle at the top. We will, for now, refer to the radius at the top as r sub 1, and the radius at the bottom as r sub 2. And the length from the top circle to the bottom circle along the side, we will refer to that as L. Okay, so if we consider the full cone, so once again, not quite to scale, but let's consider a cone that we had before we created a frustum. So the radius of the circle on the bottom is r sub 2. The radius of the circle on top is r sub 1. This length, we're referring to this length as L. So this length up here, we will refer to this as L sub 1. So can you think of a way to find the lateral surface area of the frustum using what we know about lateral surface areas of cones? So in general, the lateral surface area of a cone is pi times the radius times L, where L is, in this case, is the entire length. Okay, so the lateral surface area of this frustum, just in words, is the lateral surface area of the big cone minus the lateral surface area of the small cone. So I'll write that down. The lateral surface area of the frustum is equal to the lateral surface area of the big cone minus the lateral surface area of the small cone. Okay, I'll get out another piece of paper, and then we'll write out what this equation is. So for reference, I'll just rewrite the lateral surface area of a cone in general, pi times r times L. So here's a cone, lateral surface area. So here's another one of those. Okay, and the area of the frustum is equal to the area of the lateral surface area of the big cone minus the lateral surface area of the small cone. Okay, so now we can write down the lateral surface area of the frustum. The lateral surface area of the big cone, well, for the big cone, we're using radius r sub 2, so it's pi times r sub 2. And on the big cone, the length of the length or the distance from the tip to the circle is the quantity L1 plus L. And then from that, we're subtracting the area of the small cone. So for the small cone, it's pi times the radius r sub 1 times L sub 1. Might help if you can see what I'm doing. Okay, we'll do some algebra with this expression on the right-hand side. So the area of the frustum. So distribute multiplication by pi times r sub 2, and we get pi times r sub 2 times L sub 1 plus pi times r sub 2 times L minus pi times r sub 1 times L sub 1. Two of the terms have L sub 1 in it, so we'll group those terms together. And we'll write this as pi times r sub 2 times L sub 1 minus pi times r sub 1 times L sub 1, and then plus pi times r sub 2 times L. And in the next step, we'll factor out of the first two terms, we'll factor out pi times L sub 1. But I'll keep the same form. I'll put the r sub 2 minus r sub 1 in the middle, and then pi on the left and L sub 1 on the right. Okay. Well, if you consider just the frustum, it's not that hard to determine what the radiuses r sub 1 and r sub 2 are. And it's not that hard to determine what L is. But if we can find a way to replace L sub 1 with something that it's equal to, so that we get an area of the frustum in terms of r sub 1, r sub 2, and L only, that would be preferable. Okay, the way we're going to do that is by using similar triangles. So if we were to take a cross section of that cone so that it forms right angles with the base, then part of that cross section would look something like this. So these are right triangles that are similar. So this length up here is r sub 1, this is r sub 2. This side is L sub 1, and this one is L. Okay, so using similar triangles, for the top right triangle, we can write down that L sub 1 divided by R sub 1 is proportional to L sub 1 plus L divided by R sub 2. Okay, so what we're going to do is we're going to solve this equation for L sub 1, and then in the equation above that, we're going to replace L sub 1 with that quantity. So if two fractions are equal, the cross products are equal. So one cross product is L sub 1 times R sub 2. The other cross product, whoops, this should be L sub 1 plus L only. That's the length of this side, L sub 1 plus L. Okay, so one cross product, L sub 1 times R sub 2, is equal to the other cross product, L sub 1 plus L times R sub 1. And then L sub 1 times R sub 2 is equal to L sub 1 times R sub 1 plus L times R sub 1. Then we'll subtract L sub 1 times R sub 1 from both sides. So L sub 1 times R sub 2 minus L sub 1 times R sub 1 equals L times R sub 1. Then factor L sub 1 out. We get L sub 1 times the quantity R2 minus R1 equals L times R sub 1. And finally, L sub 1 is equal to L times R sub 1 divided by R sub 2 minus R sub 1. Okay, so now we're going to combine the results of this equation for the lateral surface area of the frustum and this equation solved for L sub 1. So we can write the area of the frustum, lateral surface area of the frustum, it's equal to pi times R sub 2 minus R sub 1. Replace L sub 1 with L times R sub 1 over R sub 2 minus R sub 1. And then plus pi times R sub 2 times L. So we get a nice cancellation. The factor R sub 2 minus R sub 1 from the numerator divided by R sub 2 minus R sub 1 from the denominator equals 1. So we're getting closer to the lateral surface area of a frustum. So now we have pi times L times R sub 1 plus pi times R sub 2 times L. And we'll write this as, since both terms have common factors of pi and L, we'll write this as pi times R sub 1 plus R sub 2 times L. Hey, this is a pretty nice formula for the lateral surface area of a frustum. So just to point that out, if we have a frustum we can find the radius of the top, that's r sub 1, and the radius of the bottom, r sub 2, and the length of the side, L, then the area is just pi times r sub 1 plus r sub 2 times L. Hey, but we're going to do one more thing. Notice that if we let R be the average of r sub 1 plus r sub 2, let R be equal to r sub 1 plus r sub 2 divided by 2, then 2 times R is equal to r sub 1 plus r sub 2. And then our formula for the lateral surface area of a frustum can be written as 2 times pi times R times L. And then we want to remember that R is just the average of the two radiuses, r sub 1 plus r sub 2 divided by 2. Hey, this is a pretty nice formula for the lateral surface area of a frustum. Okay, we're going to use that to derive a formula for finding the area of a surface of revolution. Okay, so that's what we're going to do next. So if we let y equals f of x be positive, by which I mean f of x is greater than 0, such that f prime is continuous, okay, so we will rotate y equals f of x about the x-axis for values of x between a and b. So if we rotate it about the x-axis, it will generate a solid with a surface, and we want to find the surface area. Okay, so find a formula for the surface of, for the area of the surface of revolution. Okay, so we're going to divide the interval from A to B. Point B is the same as x of n. And we have n subintervals. We'll just look at the ith subinterval. So I'll mark this one as x sub I minus 1 and x sub I. And then we have the graph of some function of x. So this is the graph of y equals f of x. And the first thing we want to think about is what will the surface area be if we rotate this portion of the curve about the x-axis. And if we can find a formula for the surface area on this interval from x sub I minus 1 to x sub I, then all of the other surface areas on all of the other intervals will have the same form. And then we can just add them up, and that will be an approximation for the surface area. Okay, on the graph of f of x, corresponding to this point is the ordered pair x sub I minus 1, f of x sub I minus 1. And corresponding to this point on the graph is the ordered pair x sub I, f of x sub I. And then if I draw a straight line segment connecting those 2 points on the graph, so tell me, if I rotate both the curve and this line segment about the x-axis, so one complete revolution around, well, let's ignore the curve f of x and just focus on the straight line. So what sort of figure is going to be formed by rotating this line segment about the x-axis? A frustum. Yeah, a frustum. And if we can find the lateral surface area of that frustum, that will be an approximation of the area of the surface of revolution for the curve on that interval. Okay, so let's let S sub I be the exact area of the surface of revolution when we rotate y equals f of x on that interval. So let S sub I be the exact area of the surface of revolution. For y equals f of x, when we restrict it to the interval x sub I minus 1 to x sub I. Okay, so that means S sub I is approximately equal to the lateral surface area of the frustum that we get when we rotate this line segment about the x-axis. So up here, I'll use as a reference the area, by which I mean lateral surface area of a frustum A sub f for the lateral surface area of a frustum. So what did we get? One way to remember it is 2 times pi times the quantity of the sum of the two radiuses. We could write it, whoops. Since I wrote 2 pi, I need to write r and then times L, where r is the average of the two radiuses, or equivalently, pi times the sum of the radiuses, r sub 1 plus r sub 2 times L. Okay, so what are the radiuses of the frustum when we rotate this line segment about the x-axis? One radius, this radius is f of x sub I minus 1, and the other radius is f of x sub I. So we could write the surface area of the function of the curve rotated about the x-axis on that interval is approximately equal to pi times f of x sub I minus 1 plus f of x sub I, and then multiplied by L. L is just the length of this line segment, so we can use the distance formula for that. That's the square root of the quantity x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared. So this quantity we dealt with yesterday, so we'll transform that the way that we did yesterday. Okay, and let's see. Before I abandon the picture, so it's pretty obvious when we look at the values between f of x sub I minus 1 and f of x sub I that there's some number x in this interval at which it's equal to the average of those two numbers. So we'll write this as 2 pi times f of x sub I star, where f of x sub I star is the average of f of x sub I minus 1 plus f of x sub I. And then we'll do, instead of going through the whole process again, we'll just replace the square root of this quantity as the square root of 1 plus f prime of x sub I star squared times delta x. So for intervals that are small, these two numbers, x sub I star, are approximately the same. So there's no harm in referring to them as the same point because the intervals are so small. Okay, so this is an approximation of the surface area that we get by rotating y equals f of x about the x-axis on this interval. And so the entire surface area of revolution is approximately equal to the sum that we get from all n subintervals. So from I equals 1 to n of 2 pi times f of x of I star times the square root of 1 plus the square of f prime of x of I star delta x. And then when we take the limit by letting n go to infinity, we get the formula. So it's the definite integral from a to b of 2 pi times f of x times the square root of 1 plus the square of f prime of x dx. Okay, we're out of time. I'll just write one more thing. This is the area of a surface of revolution formula. Okay, so tomorrow we'll do some examples using this formula. Okay, but that's all for today. So go ahead and sign in for attendance. Thank you.